All right, so this one is going to be a little small, miscellaneous, fairly quick topic. I believe your homework for the integration using data, it's just the backside of your average value worksheet. So you do need to do it. It's pretty quick. It's not too bad. A lot of it's pre-cal skills, but we're going to kind of power through this one page in the notes. And conceptually, it's going to give us an opportunity to kind of get into something that's very important. Okay, it says water is flowing into a tank over a 24-hour period. The rate at which water is flowing into the tank at various times is measured, and the results are given in this table below. And it says R sub t is the rate function. That's measured in gallons per hour, and t is measured in hours. It tells us the tank contains 150 gallons when time equals 0. That's great. And here it's going to give us another opportunity. We've seen this in the past, but it's going to give us another opportunity to hit this big conceptual nail on the head that the integral of a rate or a rate of change is your amount of change. Right? An integral itself, right? If you're integrating f prime, right? Think about your fundamental theorem of calculus. Integrating f prime from a to b, that's f of b minus f of a. F prime, that's the rate of change, right? It's the slope. Integrating the slope, right, gives you that total change in the y values, f of b minus f of a, right? That's your rise in your graph. You think about the slope. It's not the rise over the run, that's the whole slope, but integrating the rate of change is going to give you your amount of change. The area bounded by the derivative, that's how much your y values either go up or you go down, right? From one point to the next, does your graph go up or does your graph go down? Well, that's going to depend. Do you encapsulate positive area or do you encapsulate negative area, right? The integration of the rate is your amount of change. And that applies to just purely conceptual or purely mathematical things like your fundamental theorem of calculus. It also is going to apply to these word problems. If we have this function that's giving us the rate flow of water, right, gallons per hour, if I integrate it, remember what integration's doing is you're adding together infinitely many instantaneous values, right? So when I integrate this from 0 to 24, you're accumulating all of those hundreds and millions and trillions of momentary values over that interval. And if you accumulate the rate, gallons per hour, over the course of hours, what it's going to give you is how many gallons come into the tank over that time period. If this was flowing out, it would be the outflow amount. But the integral of the rate is the amount to change. So when I integrate R sub t, which is the rate of water flow, it's going to tell me how much water either flows in, if it's an inflow function, or flows out, if it's an outflow. Okay, so the integration of the rate is your amount of change. That's a very important thing, right? That's why it's got asterisks. That's why it's in the notes again. I think this is at least the second time, could be the third. I don't remember, but it's been in there before. The integral of a rate is your amount of change. All right, enough rambling, Mr. Bell. We only got 4 examples on this whole video. Let's go for it. Let's get it done. Let's get it done. Part A, estimate the number of gallons of water in the tank at the end of 24 hours by using a midpoint Riemann sum with 3 subintervals and values from the table, blah, blah, blah. Okay, show you computations, of course. What does it want? The number of, how much water is in the tank at the end of 24 hours, midpoint Riemann sum, 3. Okay, so midpoint, 3, Riemann, I know what to do, right? Here we go. The change in the water, the amount of change, that's found by integrating your rate of change. Specifically, if we want the change in water from 0 to 24, then I would have to integrate from 0 to 24. Right? So that integration from 0 to 24 would be the exact change in water. How much water comes into the tank? We are going to approximate it by doing a Riemann sum. Now let's see. It says 3 subintervals with, and it doesn't specifically say equal, but why would you, right? You could do this, then that, and then that. But like if you can make equal subintervals, you might as well. So we're going to do 0 to 8, then we'll do 8 to 16, then we'll do 16 to 24. Right? We're going to make it so that the width of each rectangle is the same. So here we go. The first interval will be 0 to 8. The second interval, 8 to 16. Third interval, 16 to 24, right? And you can see how each one of those is going to have a width of 8, so I'm going to have that universal width factored out. And then look, right, if you were doing a left Riemann sum, you would use the 8. If you were doing a right Riemann sum, you would use the 9.3 for the height. Since we're doing a midpoint Riemann sum, the midpoint of that interval would be 4, and that number's right there for you in the table, right? The height of that first rectangle, since we're doing a midpoint Riemann sum, it's not the 8, nor is it the 9.3. Since we're doing the midpoint, you use the number at the middle, right? So we're going to use 8.8 for the height of that first rectangle. If you focus on one interval at a time, your life should be easy. The next interval is from 8 to 16. The midpoint of that interval is 12. Therefore, I'm going to use 9.2 as the height. If it was a left Riemann sum, you'd use the 9.3. If it was a right Riemann sum, you would use the 8.9. Since it's the midpoint, you can use the 9.2. And then the last interval is from 16 to 24. So if I was doing a left, I would use the 8.9. If I was doing a right, the 6.7. But now, since I'm doing a midpoint, 8.1. If you focus on one interval at a time, these Riemann sums should really never, ever, ever be difficult because they're just areas of rectangles or areas of trapezoids. Geometry should be easy by the time you're in calculus, hopefully. Okay, imagine me typing this into the calculator. 8 is 8. All this stuff on the inside would give us 26.1. Multiply it by 8. And so we end up getting 208.8 gallons. Now, that is not the answer that the question wants, right? What 208.8 gallons, what that represents, is how much water has come into the tank over this time period, right? The integration of the rate is your amount of change. So 208.8, that's how much comes in over that interval. Sometimes you will get questions that only ask, hey, student, how much water comes in? Or if it's an outflow function, how much water has leaked out of the tank? Right? Sometimes you get questions that ask purely, what is the amount of change? Either how much comes in or how much has gone out. But that's not what this question wants. Right? This question wants how much water is in there at the end, right? It wants that final quantity. So what I'm going to have to do with this 208.8 is I'm going to have to add it to the 150, right? We had that initial amount, and I would either add to it if you have an inflow, or I would take that initial amount and I would subtract from it if we had an outflow. So here I'm going to take that and I'm going to add the 150 and we're going to get 358.8. That is approximately how many gallons of water are going to be in the tank at the end of this 24 hours. Approximately, because we used the Riemann sum to guesstimate how much water comes in. But we started with 150. The integration told me about how much comes in. So I take the amount that comes in, add it to how much was in there, and then that will give us that guesstimation for how much is in there at the end. Be careful. Be careful and read the question. Is it asking for just the change, or is it asking for the amount at the end after the change? If it's asking for that final quantity, you either take your initial and add to it, or you take your initial and subtract from it. Here we're adding since we had an inflow. All right, part B is the same thing, but it's doing a trapezoid instead. Okay, so we have the change in water is the integration, which we're going to approximate by doing a Riemann sum. Of course, trapezoid, remember we have 1/2 base 1 plus base 2 times the width. I'm going to factor out the 1/2. We also are still going to have the same intervals, right? It says 3 trapezoids. So I'm still going to have the same intervals. 0 to 8, 8 to 16, 16 to 24. So I'm still going to have that 8 factored out. And let's look. For the trapezoidal, this would be the base 1 for the first one. And then the 9.3 would be the base 2. Right, so I'd use those two numbers. Then in the next trapezoid, which is from 8 to 16, that would be the left side, that would be the right side. Then for the last interval, that would be the left, that would be the right. So the 8 gets used once. The 9.3 and the 8.9, they get used twice. And then the 6.7 gets used once. You don't use every single numbers. But the ones on the end get used once, and the ones that you use in the middle, they get used twice. You add them together, multiply it by 2. Then kind of just envision me typing all this into my calculator. I guess we have the 1/2 in the 8, so that'd be 4, and then we would get 4. And then all this stuff from the summations of the heights. That's 51.1. And so what we would end up getting is 204.4 gallons. That's how much water comes into the tank over that time interval. And then, of course, this is asking for the final amount. So I would, again, add the 150 to it. So we'd have 354.4 gallons. That's approximately how much water will be in the tank. If you take your initial, add in the amount to change, there we go. Okay, now 2 more parts and then we're done. Part C, it says, forget about the table, right? Remember, the table was R. R was our rate flow function. It gave us some data points, but it says, okay, now forget about the table. Now we have a model for this function given by W. So W is now our rate function. And instead of just having data points from it, we actually have the whole shebang, right? We actually have that W function. And it says use this model, W, forget about the table, forget about R, it's dead to me. Use the function W to find the number of gallons of water in the tank. Okay, so this is the same thing. I'm going to find the change in water by integrating from 0 to 24, but now I'm no longer going to have to approximate it. Now I can just math 9 this sucker to get that exact value for the change in water. Okay, so change in water, again, that's the time interval, 0 to 24. I probably should have wrote that here. It was 0 to 24. But now instead of estimating it by integrating R, now we're going to get that precise value by doing the math 9. So math 9 with my graphing data calculator. If you have the function that's named, like you don't have to rewrite it. If you wanted to, you could do 1 over 75, 600 plus 20t minus t squared. Like you could go through and you could write out that whole function again, but you don't have to. Okay, if the function is named for you, you're welcome to just use the name of it, right? It saves you some time on these free response on the AP exams. Don't write out W, just write W, right? Now, you would probably want to type that into Y1, and then you could integrate Y1, but that's okay. You could either write it all out, or if it's named W, you can just say, hey, I'm going to integrate W, and then I'm going to use my calculator to get it done. Now, if I integrate it, I would get 207.36. That's the amount of water that comes in. And then, of course, I would have to add the 150 to it because it's wanting what's that final amount. And so here we would get that final precise amount is 357.36 gallons. That is no longer an approximation, right? Those were approximations. This is just equals. That is the exact amount of water that's in there at the end of this 24-hour period. We were no longer approximating the change with the integral, with the Riemann sum. Here we actually did the exact integral with the calculator. Could have done it by hand, but they were kind of biggish numbers. You can tell because of the decimal is nasty too. But we got the exact value by using the integration in the calculator. Last part, and then we're done. It says use the model given in C. So use W to find the average rate of water flow. Okay, there's 2 ways you could do this. You could do it kind of geometrically. You could think, okay, rate of water flow. I guess this is more algebraically. Rate of water flow would be your change in water over your change in time. So that's how much water comes in over how long was it coming in. We already know this, right, from previous, right? That's the integration. The change in water is your integration. The change in time was, 24 minus 0. So we had this already. It was your 207.36 divided by 24, right? That's how much water comes in. 24 hours was how long it was coming in. So then we could get this average rate of water flow. We could be 8.64 gallons per hour, right? That's gallons. That was 24 hours, so of course your units would be gallons per hour. You could do it that way, right? The rate of water flow is the change in water over the change in time, which is how much water comes in over how long it is coming in. That's a perfectly good way to do it. There's another way, though, right? Think about it like this. If you want average rate of water flow, you could do the average value of the water flow function. Right, that makes sense. The average, oops, I'm off the screen. My bad. The average rate of water flow is the average value of the water flow function. Remember, that water flow function was given to us by W. So we could do 1 over 24 minus 0 over 0 to 24 of your W function. Right? That's your formula for average value, 1 over b minus a. Then you do the integration from a to b. The average value of your water flow is the average water flow. Now here, this should be the 1 over 24. This we know is the 207.36. And then 207.36 with the 1 over 24, that's going to give you the same thing. Now let's look at it. Right? The average rate of water flow versus kind of this rate of water flow that we did more just analytically, thinking about the change in water over the change in time. Why did we get the same thing? This and this are the exact same thing, right? Here it's just got it written on the top, here it's on the right, here it's got it on the bottom, here it's over there on the left. But whether you do the integral divided by the time interval that elapses, or whether you have the time interval out in front and then the integral, you're going to get the same thing. We're trying to figure out how much water comes in over how long it is coming in. If your brain works more like this, great, it'll work. Or if your brain works more with the average value, it'll work, right? Two different ways, equally as valid, to get this question done. Since we just did average value, this way is probably hopefully the way that's really fresh for you. But doing the just more analytical, hey, rate of water coming in, that's the change in water over the change in time. If your brain works more like that, that's wonderful. You should be able to get the same answer. But doing the average value of the water flow function will also work. Those two things are the exact same, so of course they give you the same number. Okay, that's it for this video. Homework should be a little bit annoying, but not terribly difficult.